You know, we hear the term microplastics all the time. It feels like they're everywhere. But have you ever stopped to think about how scientists actually find something that's practically invisible? And what if the answer wasn't just to filter them out, but to get them eaten? Well, today we're pulling back the curtain on the entire scientific procedure, from hunting for clues to hiring a microscopic cleanup crew.
And before we get into the how, let's just ground ourselves in the why. This isn't just some neat science experiment. The stakes are incredibly high. This number right here is what drives researchers to develop these complex, meticulous procedures we're about to walk through.
So let's be crystal clear on what we're actually looking for. Microplastics. We're talking about tiny little fragments of polymer, anything smaller than 5 millimeters. To give you some perspective, that's about the size of a single grain of rice, and often they're much, much smaller. That's what makes this whole process such a massive challenge.
So here's the game plan. First, we're going to play detective and look at the whole procedure for finding and identifying these plastics. Then, we'll switch gears and explore a really cool potential solution, using bacteria to do the hard work for us. And we'll wrap up by looking at the one giant hurdle the entire field is facing right now.
All right, let's get into the investigation. You know, people say it's like finding a needle in a haystack. Honestly, this is way harder. This is like finding a specific invisible fleck of dust in a hurricane. I mean, really think about that. How on earth do you even start? The problem is so huge, and the target is so small that you can't just wing it. You need a rock-solid, step-by-step procedure just to get your hands on a sample worth studying. The whole method follows this classic investigative framework. It's a logical flow, and you absolutely cannot skip a step. First, you've got to collect the evidence. Then, you have to isolate your suspects, the plastics, from everything else. And only then, once it's all alone, can you identify the culprit.
Now, how you collect that evidence really depends on your crime scene. If you're on a beach, you might just do some selective sampling, literally picking up visible fragments. But if you're looking in lake mud, you'll do a bulk sample, kind of like taking a core sample of the Earth. And in the open ocean, you have to do volume-reduced sampling, which means dragging these superfine nets through the water for miles just to concentrate enough particles to study.
Okay, great. You've got your bucket of ocean water or your bag of sand, but now it's just a messy cocktail of sand, seaweed, dirt, and hopefully, plastic. So the next critical step in the procedure is separation. You have to get the plastic away from all that other natural stuff.
And scientists have some really clever ways to do this. Sieving is pretty straightforward. You just use filters to separate things by size. But density separation is, frankly, genius. They take the whole messy sample and mix it into this incredibly dense, heavy liquid. It's so heavy that sand and rocks sink right to the bottom. But the plastics, being much lighter, just float right to the top, where they can be skimmed off easily.
So, you've isolated a tiny particle. Awesome! But the job's not done. You have to prove what it is. Is it from a water bottle? A car tire? This is where the procedure moves into the forensics lab to figure out that particle's unique chemical fingerprint.
And they have some seriously cool gadgets for this. A scanning electron microscope, or SEM, is like a super-powered magnifying glass that gives you these incredible images of the particle's surface. Then you've got FTIR, which shoots infrared light at the sample. Every type of plastic absorbs that light differently, giving it a unique fingerprint. And if you need the full story, you use PyGC/MS. That one actually torches the plastic and analyzes the smoke to tell you exactly what it's made of, down to the last additive.
Okay, so we've just walked through the entire procedure for finding and identifying the problem. But what about fixing it? Let's shift gears now, from detection to a possible solution. And it's a wild one: recruiting an army of microbes to clean up our plastic mess.
Here's the thing about plastic. Its greatest strength is also its greatest weakness. It's designed to last forever, and in the environment, that's a nightmare. It just sits there for hundreds of years. So a ton of research is now focused on finding something, anything, that can hit the fast-forward button on that breakdown process. And the best candidates might just be tiny microorganisms.
And guess what? The procedure for finding these little helpers looks strangely familiar, doesn't it? It's the same basic scientific method we just saw. Collect your samples, isolate what you're looking for, and then identify it.
So if you're looking for bacteria that can eat plastic, where do you go? You go where the plastic is. The thinking is pretty simple. Go to places like landfills or plastic-polluted soil, where microbes have been living with this stuff for decades. The hope is that, over time, some of them have evolved and learned to see all that plastic not as trash, but as lunch.
Now, this step in the methodology is my absolute favorite.
It is so smart. To find the specific bacteria they want, they create this special liquid growth medium. It has all the basic nutrients a microbe needs to live, except for one thing, a source of carbon, their food. The only source of carbon they add to the mix is finely ground up plastic.
So it's basically a bacterial Hunger Games. If a microbe can't figure out how to eat the plastic, it starves, simple as that. The ones that survive and start to multiply, those are your champions. And this enrichment procedure is incredibly effective. It's how researchers have found some of our best candidates, like species from the Bacillus and Pseudomonas families.
Okay, so you've found some survivors. But that's not enough. In science, you need cold, hard proof. The next part of the procedure is all about verification, designing experiments to prove, without a doubt, that these bacteria are actually eating the plastic. And the most straightforward test? It's a weight loss experiment. It's beautifully simple. You weigh a piece of plastic very precisely, you introduce it to the bacteria, you wait, and then you weigh it again. If the bacteria are doing their job, that plastic should be lighter.
And the results can be pretty dramatic. One study put some Pseudomonas bacteria to work on plastic samples. In just 120 days, the plastic lost 25% of its total weight. I mean, think about that. A quarter of the plastic was just gone, eaten.
And if the weight loss isn't convincing enough, you can just look at the visual proof. Remember that SEM microscope from before? Scientists use it here too. Before the bacteria get to work, the plastic surface is smooth and clean. But after, it's a war zone. The surface is covered in pits, holes, fractures. It's clear, visible evidence that the microbes have been tearing it to pieces.
So we've covered the entire procedure, from the hunt for the problem to testing out a really promising solution. But there's one last, huge, overarching challenge that affects absolutely everything we've just talked about.
And this quote nails it perfectly. Right now, different labs all over the world are using slightly different procedures. One team might use a net with a certain size mesh, while another uses a different size. One uses zinc chloride for separation, another uses something else. And because of that, you can't really compare their results directly. It's like everyone is speaking a slightly different dialect.
So in the end, the biggest hurdle might not be the science itself, but the methodology. The challenge isn't just finding more plastic-eating bacteria, it's getting everyone to agree on one single, standardized way to look for them and for the plastics themselves. It's about creating a global playbook that every scientist can use, because we can only truly solve a problem when we can all agree on how to measure it in the first place.